Hi class, this is a second video on blackbody radiation and using Wien's law to relate a blackbody's Kelvin temperature, so that's its temperature on the Kelvin temperature scale, and the wavelength at which its spectrum peaks. And in the first video, we were given a temperature. We were given the temperature of a light bulb filament of 3000 Kelvin, and we calculated lambda max. So just quickly looking back at that video or that calculation right here, we took Wien's law, we plugged 3000 Kelvin into it, and out came a wavelength of maximum emission of 0.97 micrometers. We also converted that into nanometers, so we got an answer of 970 nanometers, and we identified that as being in the infrared, because you'll remember that the visible part of the electromagnetic spectrum that we can see with our eyes, that ranges from around 350 at the short end, that's violet light, up to 700 at the long end, that's red light. So 970 is longer than 700, so it's in the infrared. And so that was fun. In this video, we are going to kind of flip this around. We're going to be given a lambda max, or we're going to look at a spectrum and we're going to identify lambda max from the spectrum, and from that we're going to calculate the temperature of the object. And this is a very important object to us. This is the sun that we orbit around here on Earth, and this is the spectrum of light from the sun. So you take an instrument called a spectrometer and you point it at the sun and you measure how bright the sun is. So that's on this scale at all these different wavelengths, and these wavelengths are in nanometers. And so you identify, this is 700 nanometers right here, this is red light, this is 350 right there, that's violet. So this is the visible part of the electromagnetic spectrum. This is all infrared light, and this is all ultraviolet light. So the sun does emit quite a bit of ultraviolet light right here. Fortunate for us, here on Earth, we have this thing called the ozone layer, which is a layer of molecular oxygen in our atmosphere, and that's responsible for the most part in blocking this very harmful ultraviolet light from the sun, and that's why we can live down here and survive. Anyways, you look at the spectrum of the sun and you kind of blur your eyes a bit, or you have a computer do this, and you fit this to a blackbody curve, and then you identify that this right here is the wavelength at which the sun, at which its spectrum peaks. And you look down here, that's a wavelength of 500 nanometers. That's green light. So actually the sun primarily emits green light because that's where its spectrum peaks. Now we can use that, so here it is. So here's the observed wavelength of maximum emission of the sun, 500 nanometers. That's 500 times 10 to the minus 9 meters. That's what a nanometer means. And then what we can do is we can clean this up and put it into what's called proper scientific notation. So we want to take this number 500 and we want to make it between 1 and 10. So we drop it down to 5 and make it 5.0. And since we made this part of the number smaller by 2 powers of 10, we make the exponent part larger by 2 powers of 10. So we add 2 to negative 9, it becomes negative 7. So these are this, and this. These are all the same number right there. Well, actually, these are the same number. These are the same wavelength, but that's expressed in nanometers. All right. So anyways, we got the wavelength from 500 nanometers to 5 times 10 to the minus 7 meters. And now what we can do is we can take Wien's law, but we want to rearrange it. We want to use algebra to rearrange this because we have lambda max. We want to solve for t. We want to figure out what t is for the sun. So you drag the t up here and the lambda max down there. Use some cross multiplication, and this is it. So this is the same equation, but we've solved it for temperature. So now you can take this number 0.0029 and you can divide it by the wavelength of maximum emission. And that's what I'm going to do right here in the next slide. So we can take this number and we can put it into scientific notation like we've done before, turn this into 2.9 times 10 to the minus 3. We take the wavelength of maximum emission, 5.0 times 10 to the minus 7, and put it down there, and now we do the calculation. So 2.9 divided by 5.0, your calculator will tell you that is 0.58. And then we got to deal with the exponent. So we're going to have times 10. We take the top exponent minus the bottom exponent. And this is a little bit weird right here. And this is where I always see students make mistakes. So listen up. Ready? -3 minus -7. When you hear that minus negative, that's like a double negative. You replace that with plus. So this is really -3 minus -7 is the same thing as saying -3 plus 7, which is +4. So this becomes times 10 to the 4. And to put this into like regular notation, this is 0.58 times 10 to the 4. 10 to the 4 is 10,000. So 0.58 times 10,000 turns out to be, right here, it's 5,800. You move the decimal place 4 spots to the right and you fill it in with zeros in those 2 spots right there. So there it is. Based on the observed wavelength of maximum emission, 500 nanometers for the sun, you convert that into meters. You rearrange Wien's law to solve for temperature, and then you do the math, and you get the temperature of the sun just by looking at it and taking a spectrum, 5,800 Kelvin. And this is a very important number. We're going to be using this all the time in the future in this class, but that's where it comes from for the sun. And you'll notice that the 2 examples we did, so you got radio and microwave. Previously, when we talked about wavelength and frequency, we did a few examples of radio and microwaves. Now in blackbody radiation, we've had some examples where we did the light bulb example, which had a wavelength of 1 micrometer. That was right here in the infrared. And now we just did an example for the sun where we saw that lambda max for the sun was green light. So that's right here, 500 nanometers. And taking a quick look at our Chapter 5 homework assignment, this material that we just covered, blackbody radiation, that's relevant to these problems, number 3 and number 4. So problem 3, I give you a wavelength 700 nanometers, calculate the temperature. So this is very, very similar to the calculation we just did for the sun. Except for the sun, it's observed to be at 500 nanometers. Now we're talking about a star which is at 700 nanometers. Or I guess I just left it general as an object, but there's many stars out there which have their blackbody spectra peak at 700 nanometers. So this is very relevant to studying stars. And then question number 4, this is very interesting right here. A white dwarf star, and we will be reading about this in chapter 20 when we read about how stars die. But a white dwarf star is, that's the name given to it's actually not a star, it's actually the core of a dead star. So it's the exposed core of a dead star which has shed its outer layers and it's exposed its very, very hot inner core. So anyway, we'll come back to this in chapter 20, but we can do some math on this. There's one particular really striking looking white dwarf star. It's at the center of a planetary nebula. I would encourage you to Google this or look this up in your textbook, the Ring Nebula, and look at it. At the center of the Ring Nebula is a white dwarf star, and that white dwarf has a temperature of 125,000 Kelvin. So what I want you to do is take this temperature. So this is 125,000. This is 1.25 times 10 to the 5th. And I want you to take this temperature and plug it into Wien's law and calculate the wavelength of maximum emission and express that in both meters and then convert it into nanometers. And this will be a very interesting result. We'll talk about it more as we talk about problem 5, and also in future chapters. We'll keep coming back and referencing this calculation. So I'd really like you to put some thought into this. Okay, I will see you in future videos.